by any signal that if you can't hear me clearly. Sub and supercritical water technology for biofuels. Sub and supercritical water, in a way we call it also as hydrothermal processes or hydrothermal technology, and how it can be applied in producing biofuels. So I would like to thank Gaurang and the ICT team for arranging this talk. And let me tell you first why we need biofuel first, and then I will introduce you to sub and supercritical water technology or hydrothermal technology, what it is, and how this technology can be applied to producing biofuel in much greener environment with minimum chemical footprint. So first of all, why alternative or renewable fuels? We all agree on that we need energy independence or energy security. This is a vital part of our daily lifestyle. Second is diminishing fossil reserves, because right now we depend mostly on the fossil fuels and it's not unlimited. There are many reserves coming up, but they are limited only. They are going to diminish it. The third concern is environmental concern. Because of the nature we use fossil fuel nowadays, coal, petroleum products, natural gas, we introduce extra CO2 every day to the environment. So these are the three major concerns, and I would like to start with how we depend on our fossil fuels. In this graph, I am trying to show you the trend from 1970 to 2010, last 40 years or so, how it has been the trend in use of coal, oil, natural gas, nuclear, hydropower, and part of it is biofuels. As of here, you can see that most of the energy for our use for last 40 years has been coming from the use of coal, natural gas, and oil. And this y-axis, I see the units which gives you the million tons of oil equivalent. That means energy equivalent to from many other resources. Suppose coal, how much energy equivalent to the use of the oil, how much energy we get from the use of the oil. So this shows that clearly we can see that we typically depend more than 80% for our energy use on fossil fuels. Let's see the proportion of this fossil fuel, how we get it. In early 70s, oil was contributing 46%, natural gas was 16%, coal was nearly 25%. Again, you can see that a lot of dependency was on this fossil fuels. Again, this is from 2010, the energy use almost doubled, 6,000 million tons of oil equivalent to nearly 12,000 or 13,000 million tons equivalent, oil equivalent. But our nature of use is, again, we heavily depending on the oil. It's slightly reduced because natural gas caught up in between, and the use of natural gas has started a lot. The coal, so these three again compose more than 80%. And we all know that these are fossil fuel. That means form of carbon which was buried below the ground, and with the use of this fossil fuel, this carbon is coming up, which is not sustainable. So when I am saying that which is not sustainable, because fossil fuels are limited, and the environmental concern, all of us, we know the greenhouse gases. If you see the carbon dioxide emission, which is one of the primary greenhouse gas, majority of it comes from fossil fuel use, 57% of it. And there are other contribution from deforestation and all, but the major contributor of carbon dioxide is fossil fuel use. Who are contributing more? Most of the developed or fast developing country. We can see the US, European Union, China, India is catching up. So how it goes? We develop. As we develop, we use more energy. More energy. There are not much other alternatives, so we heavily depend on the fossil fuel. And fossil fuel again contributes to the carbon emission, carbon dioxide emission. When we burn natural gas, it's carbon dioxide, coal, carbon dioxide emission, oil, carbon dioxide emission. And why we should worry? Because this carbon was buried below the ground and now we are drilling or mining to bring it up, and it goes to the environment for a long time. So as a result of it, in the last 40 years, we can see that carbon dioxide emission has gone up very heavily. If you see that the carbon dioxide in the atmosphere was around 310 ppm parts per million in 60s, the last year it was measured around 393 ppm, 395 ppm. So one thing we cannot deny that CO2 in the environment is increasing. That's one of the main greenhouse gas. Now there can be debate, this is the reason for global warming or not, or climate change or not. There are two aspects of it, some say no, some say yes, but we cannot deny this fact that the CO2 concentration has gone up higher in last 40 years. And this measure, again I say that this came from the fossil fuel use. So what is the one of the alternative to improve our energy security or energy independence and to address the environmental challenges or environmental concern? The world and we should be developing or looking for more renewable energy options. As one of the prime data from United States, I am trying to show you here how much is the renewable energy, which is one of the developed country United States, and how much we use it here. This is just 9%. If you see that petroleum, natural gas and coal consist of majority, 8% in nuclear and 9% is renewable energy. This is total use from nearly 100 quad. One quad is 10 to the power 15 BTU. So this is from the data from 2011. And out of that, only 9% comes from renewable energy use. Now, if you say the renewable energy, this 9% consists of solar, geothermal, wind, biomass waste by burning them, biofuels like ethanol, biodiesel, wood, or hydropower. So we can see that renewable energy options are so many, and all of them in a total contribute just 9% of that. That means there's a lot of scope to make this pie bigger. There's a lot of scope to improve the solar, a lot of scope to improve the biomass, and also I'll focus my talk on biofuels. Let me come back again. What are the renewable energy sources? In the last slide, I showed you that nearly 8 or 9% is the contribution from renewable energy, and that consisted of solar, hydropower, geothermal, wind, and biomass. Now, I would like to explain you here. Suppose we use solar, what kind of energy we get? In the present time, we use solar for heating, water or heat applications, or electricity. And this slide says you what are the challenges with that. Okay, this is location dependent, this is weather dependent, what kind of weather you are, how much sun you get it. Same with hydropower. What we get from hydropower, we get electricity. So we don't run car with the electricity right now. We need liquid transportation fuel for that. So it has a limitation. And to say that what are the challenge with hydropower, it's location dependent again, how much resources you have. Here I am saying that in the United States, most of the available resources have been used or developed. Geothermal, another renewable energy option we say. This again we use for heat or getting electricity. Again, location dependent, limited availability. We don't have any control over it. Wind energy, we keep talking on that wind energy. Yes, it's a very good renewable energy option, but we use it for electricity generation. What are the challenges? Location and weather condition. How do we get it? The last option I'm going to talk is the biomass. Now let us see that what we can do with biomass. Biomass, if we burn it, we get electricity. Like coal-fired plant, biomass-fired plant can supply electricity. And we can get transportation fuel, like gasoline. We call it green gasoline, which comes from biomass. Ethanol, in US it used already 10% or 15% blend. We call it E15. That means in the United States we have to blend 15% of bioethanol with the gasoline. So this is already in use. Biodiesel, you know. So the point here is biomass, if you compare all of them, it can supply both liquid transportation fuel compared to jet fuel or gasoline or diesel, and also electricity. So it gives a flexibility and matches with the present use of our fossil energy applications. What is the challenge here? Location is not a problem. We get biomass all over the world. We know how to make ethanol from biomass. We know how to make gasoline kind of liquid fuel from biomass. We know how to make jet fuel from biomass. But why the challenge is economics, how to meet the rate of petrol or gasoline which we get from fossil fuel, how to meet that economics with biomass. So processes are there, but they are costly right now, maybe 2 times, 3 times or 4 times costly depending on what kind of fuel we are talking and what kind of feedstock we are talking. So what is the requirement here is improving these processes, making them more cost effective, lower processing costs, not only in the conversion or reactions, but also in the biomass logistic, biomass harvesting, so many aspects of it. So that's the major challenge in biomass, but good news is that we have processes which can convert biomass to biofuels. So it may take some time to come to the market to replace part of petroleum and all, because price is higher right now. We can make, I told you, we can make green gasoline from biomass, but the price is a challenge here. So with the biofuel, when I say that, what kind of fuels we are talking? In the fossil fuel regime, we are using 3 kinds of fuels. You know, coal as a solid fuel, petroleum as a liquid fuel, and natural gas as a gaseous fuel. Can we make all these 3 kinds of fuel from biomass also? Yes. Here I show you that 2 kinds of biomass. Land-based means forest residue, grasses, or agriculture residue like that, corn stover or rice stover, this kind of biomass which is being used directly burned right now inefficiently, that can be converted to different fuels. Or you might have heard about the water-based species like algae, which goes very faster. So these 2 biomass options I am going to talk, and they can be converted to liquid fuel. Examples are bioethanol, bio-crude like petroleum crude, or green gasoline, or biodiesel. You must be knowing all these things. Can we make gaseous fuel from biomass? Yes. Hydrogen, we can produce hydrogen depending on the reaction condition, how we do. We can make methane, which is comparable to natural gas. We can use biomass to make syngas. It's a building block chemical. Carbon monoxide and hydrogen composition is called syngas. And this syngas is used through Fischer-Tropsch reaction to convert to syngas to liquid fuel. So you can see that we can make gaseous fuel. Solid fuel, yes, we already use it, even in India many parts. like char material, charcoal and all. So we can carbonize biomass to make biochar and try to replace part of the coal applications. Already many part of world uses biomass for direct burning. Another option can be co-firing. The coal-fired power plants, they can use co-firing application where part of coal can be replaced with biomass and burned together for generating electricity. So you can see that all three types of fuels can be made from biomass. What could be the feedstock for this biomass? There are several categories, but I have categorized in these four types. We call it first generation biofuels and second and third generation biofuel. First generation biofuel, you will know that a starch-based feedstock, cereal grains, corn, which is used, which has a more of a starch like potato. They can be used to make ethanol, and ethanol can be used as a biofuel. Sugar cane or sugar beet, again it's a great sugar source, and sugar can be fermented to ethanol. So actually the biofuel application started with this kind of feedstocks. Even in United States, corn is used to make biofuel, but what is the challenge here is, they are called first generation biofuel. Why? Because all materials are food items. Corn is some way used for the food. Cereal grains used for the food. We don't want to divert the application to run our car. We don't want to use corn to make gasoline and run car. We don't want to divert sugar cane use for making ethanol. So that's why they are called first generation, and these applications are not being promoted because of food and fuel discussions or debates. Because if we start using these items for making biofuel, we end up increasing the food cost. That's a big challenge. So in the next generation, second and third generation biofuel we call it, which will be made for, or which are being made from forest residue like woody material, agriculture residue like rice stover, wheat stover, or energy crops. Energy crops are the crops which you grow just for the use of energy. Examples can be wheatgrass, jatropha, this kind of crops which you dedicate that kind of crop just for the energy use. This kind of crops will have a fast productivity, or they will grow faster, so you harvest it, again use for energy, grow it again. So that's kind of sustainable system. Or municipal solid waste, it's a great source of organic material. So these, you can see that the number third and fourth are the type of feedstock which does not compete with the food item. So that's why they are called second or third generation, or more commonly are being called as advanced biofuel. Advanced biofuel are made from this kind of feedstock, which are not food items. And again, I say you that using forest residue is possible to make green diesel and green gasoline. Only thing, the processes are costlier. The production cost is higher. So when we don't have a starch material or sugar material, which is direct source of sugar, if we want to use a cellulosic material like grassy material, corn stover, bagasse or chips, what they have it? They mainly compose cellulose and hemicellulose. These two are the carbohydrates. That means polymer of sugars. Cellulose is a polymer of glucose, long chain polymer. Hemicellulose is polymer of glucose or many other 5 carbon and 6 carbon sugars together. But we can see that 70% of these materials, say any grass or woody material, typically 70% are carbohydrates and roughly 15 to 20% are lignin. Lignin is called typically young coal. It's aromatic. So this kind of material, you will see that they have two major components: carbohydrates, which is source of sugar, and the lignin, which is source of mostly aromatic compounds. Let me go to the next slide now. If you want to make biofuels from this kind of materials, what are the challenges? You see the challenges here in the truck itself. It can be leaf, twigs, means very bulky, low density, or it can be woody material, slightly higher density. It can be in chips or round wood. So, what are the major challenges? Low bulk density. In the truck, we want to carry energy, not the water or this air, because it's a low bulk density, high moisture content. Any biomass you take, any grass you cut, fresh cut, any tree leaves you take, lot of moisture, maybe 50%, 60%. It's biodegradable. You cannot store for a long time in uncontrolled condition like coal and oil. Transportation is a huge challenge. This truck looks like loaded a lot, but on the energy term it may be very less. Lot of water are there. High oxygen content in biomass. So the major challenge, if you want to understand what is the major challenge in turning a biomass to biofuel, this is the oxygen content. Any fuel, but how it gives energy is hydrocarbon fuel, carbon and hydrogen gives you the energy. If you had a lot of oxygen, they will not contribute to energy. That's why the heating value goes down. So any process, if you are trying to make biomass to biofuel, our major engineering challenge, process challenge is how to remove this oxygen. This oxygen can be removed in terms of decarboxylation reaction, removing via CO2, decarbonization, removing as a CO, or by fermentation, making as an ethanol and CO2 comes out. So the biomass major challenge, if you want to take home message, is oxygen content and how to get rid of the oxygen content. Because if you remember, hydrocarbons don't contain a lot of oxygen. It's mostly carbon and hydrogen. So if you get biomass, either land-based or water-based, what are the different processes to make biofuels? Any of you know biochemical pathway. Biochemical pathway means use enzyme or organisms to do fermentation and hydrolysis of sugar and fermentation to make ethanol. That's how beer is made, from sugars. So one process is biochemical, when we use enzymes and fermentation pathway. Another is thermochemical, which refinery and oil industry knows very well, use of temperature, pressure and catalyst. What are the example of this? If you have a biomass, do combustion to get electricity, or you gasify this biomass to make syngas, and syngas then do catalytic reaction, Fischer-Tropsch, and get liquid hydrocarbons. Another process is pyrolyze. Pyrolyze means you heat in absence of oxygen. And then categorically upgrade it and get liquid fuels. So these three. Another method which I am going to focus my talk is hydrothermal. Hydrothermal is, I told you, this is sub or super application, sub and supercritical water. And through hydrothermal also means doing the thermochemical reaction in presence of water, you can say that in short. We can use subcritical hydrothermal carbonization process to make biochar, or we can liquefy biomass and then upgrade catalytically to make liquid fuel, or gasify biomass and get Fischer-Tropsch. Through Fischer-Tropsch we can get liquid fuel, or make hydrogen or methane gas. So these are the three major routes: biochemical, thermochemical and hydrothermal. I am going to focus my talk on hydrothermal. If you see that what United States is doing on what kind of process strategy, we have it here. They have taken 6 major process strategies. Fermentation, that's a biochemical route, or catalysis of lignocellulosic sugar. release sugars from biomass and do catalytic reactions, or have fast pyrolysis to pyrolyze biomass to get bio-oil, or hydropyrolysis, pyrolyze in presence of hydrogen, or hydrothermal liquefaction, use water for liquefying biomass, or a syngas distillation. And same way, cross-cutting technologies, what are the challenges here? Feedstock logistics, how to get biomass to a certain refinery, pre-treatment, separation, catalytic development, pyrolysis. So many challenges you can see that. I'll briefly go to the next slide. So what is the objective here from biomass to biofuel? Developing advanced biofuel. Advanced biofuel means which is compatible with infrastructure. Means we don't have to build a separate refinery for that or separate pipeline for that. If we can make the use of existing infrastructure, that's better. It has to be sustainable and it has to be cost competitive. So if you are doing biomass to biofuel, there are 3 insertion points are projected by Department of Energy at US. Either we make certain intermediate which can be mixed with crude oil and then goes to the refinery, comes as a final product. Example can be bio-oil production. Second insertion point can be we make certain intermediate and which goes to which is not mixed with crude oil but injected at certain point in the refining process, and then it comes as a final product together. Or third insertion point is right now which is being used partly, make bioethanol or like gasoline compatible and introduce just with the refinery product and then use same pipeline to transport and distribute. So there are 3 strategies can be adopted with biomass to biofuel. Insertion point 1, insertion point 2 inside the refinery, insertion point 3 after refining. And using these 3 approach, we can use the existing infrastructure. Then we don't have to build another infrastructure. That's a huge cost. So now I quickly I give you the introduction why we need biofuel, what are the major processes to make biofuel, what are the different feedstock. So now I'll come to the topic of my talk is how sub and supercritical water technology can be used to make this biofuel, that is hydrothermal route. So first let us understand what is hydrothermal. Suppose you boil water in open container, what happens? Water is going to vaporize. Now you put a lid over it. Make like a pressure vessel. What's going to happen? The vapors, it will vaporize, but because of pressure, again it will condense back to the liquid phase. Or density of liquid water will start decreasing if you keep heating, and vapor density will keep increasing. And there will be a point, initially it will be a 2-phase, liquid water and vapor, but there will be a point when there will be no boundary between vapor and liquid. That means density will equalize and we will have a homogeneous phase, and that is called supercritical water. So if I have to explain you what is supercritical, critical point is point beyond which the phase boundary does not exist between vapor and liquid. And what are the benefit of these critical points sub or supercritical water is, if you see this, y-axis I have a dielectric constant versus temperature, and another axis is ionization constant. So if you start hitting at a higher temperature under pressure condition, density starts dropping down, dielectric constant goes down. Dielectric constant is a measure of solvent property. Ethanol is a good solvent, acetone is a good solvent. So at 200, if you see that this water under pressure condition can be as good as methanol. Around 300 it can be as good as acetone, dichloromethane, and like hexane. So what we see that water is polar compound. okay, at ambient condition. When you start heating at high temperature under pressure condition, its dielectric constant going down, that means polarity is going down, it's becoming more non-polar, and we know the fundamental is like dissolves like. So if you have an organic material that's more polar, non-polar, so because of drop in dielectric constant, these organic materials are dissolved in water. So in a crux, if I have to say that, water at high temperature, I am saying water, not the steam. That means water in the compressed condition, density goes down, dielectric constant goes down, viscosity goes down. These three are good, important for doing any chemical reaction. Ionization constant goes up, again it's good for hydrolysis or this kind of reactions. Diffusivity increases because of lower density, so again it's good for the mass transfer. And all these properties can be tuned, that means tunable properties. Change the temperature or pressure condition, you can change the density, the electric constant, viscosity, and you can tune the reaction. So at higher temperature water, it becomes a green solvent. Supercritical water has liquid-like density and gas-like transport property, we can say that. It is highly non-polar, like hexane, it can be like as good as hexane at 500 degrees Celsius, or permits complete solubilization most organic compounds. So these are the benefits of water as a reaction medium. You can see that if you want to compare ambient water versus supercritical water, dielectric constant, which is 78 at ambient condition, goes down less than 5 as we go up in the temperature. Similarly, most of the organics are soluble, fully miscible. Oxygen solubility, we can do combustion in supercritical water because oxygen is fully miscible at high temperature. So these are the benefits of supercritical water. What can we do with this water? How can we use? So if you see that temperature versus pressure condition here, in the low temperature zone, between let's say 150 to 250 degrees C, we can use this water, which is subcritical water, good for ionic reaction, to extract many important bioactive compounds, like protein-based compounds or valuable oxidants and all, antioxidants. Slightly higher condition, we can liquefy biomass and make bio-crude. If we go higher temperature or supercritical points, let me explain you here that critical point of water is 374 degrees Celsius and 22.1 megapascal. At this point, beyond this, we will don't see the phase boundary. This is called supercritical water. So water below critical point under compressed condition is subcritical water, and above is supercritical water. Supercritical water is good for the free radical reactions, for the gasification and all. So these three zones, based on the chemical reaction what we want to do, we can tune the reactions for the desired products. What are the advantages of using sub and supercritical water? First is, I told you, the biomass comes with lot of moistures. We don't have to remove water from this. So no drying of biomass. In many processes, if you use municipal solid waste, let's say, it's not dry. A fresh cut biomass, it's not dry, lot of water. So you don't have to dry that biomass. So we save energy here if we can use that water as a solvent property to conduct our reaction. Not dependent on type of biomass. Any type of biomass we can use with this. Reduce mass transfer resistance because of the lower density and many other properties which I talked earlier. Flexibility for type of fuel, we can carbonize biomass to make solid fuel like char, liquefy or gasify. Easier product separation because we are using just water, not hexane or any other chemicals. What is the challenge? Challenge, I told you, we are talking the high pressure condition. So reactor design is a challenge here. How to pump or feed a biomass slurry in the reactor is a challenge here. And some of the salty material start precipitation, so corrosion and all. These challenges will here. The question comes energy balance. Immediately we talk about the temperature, high temperature, we think it's an energy intensive process. But it's not like steam based processes. I'll try to explain you. Most biomass contains water. If you want to compare a steam-based process versus subcritical water-based process, steam-based process means you have a vapor phase. That means phase change is required when you make a steam, and latent heat of vaporization is 2.26 megajoule per kg. If we are doing these reactions in subcritical water, that means water stays in liquid phase, so there is no phase change. So if you want to compare steam at 250 degrees C, enthalpy is 2.869 megajoule per kg. Same as subcritical water at 250 degrees C, we will require 5 megapascal to keep water in water phase, and the energy or enthalpy is 0.976 megajoule per kg. So you can see that 1/3 is required. So there is, why this benefit? Because of there is no phase change. So it may look like energy intensive, but when you go deeper into it, you see that there is no phase change. So it's not the energy intensive process. And since we do in liquid phase, it is possible to recover most of the heat also. Because when reaction is done, you just simply depressurize, and it does not have enough energy to vaporize. So we can recover most of the heat here. Now I'll quickly talk about the application. I talk why the biofuel is important, what is subcritical and supercritical water, and now how this can be applied to make liquid fuels. And these applications I'll try to give you from my own studies which I did. There are several more studies around the world, but I'll give you examples what I did in my research. If you want to make bioethanol, how we can use hydrothermal or subcritical water? Yes. If you have a woody material or grassy material, that means it has a hemicellulose, cellulose and lignin. And if you want to make ethanol, how ethanol can be made? Cellulose and hemicellulose will be the source of sugar and we will ferment it. But what to do with the lignin? We will have to separate it. How to ferment it before, how to release sugar? We will need enzymes to work on it. So to open up the structure, to make grassy material to ethanol via fermentation route, we do pre-treatment first. Water can be used to do pre-treatment. So hydrothermal pre-treatment or subcritical water can be used to do the pre-treatment. So once we do the pre-treatment, we can open up the structure. Now enzymes will work better here. So pre-treatment, why required? Rate of production of monomeric sugar which will be fermented, or yield of monomeric sugar, glucoenol, how to get it, and that will be fermented. So subcritical water can be applied here for the pre-treatment application. Let me give you an example with the switchgrass to bioethanol, how it is made. If you have a switchgrass, that is basically lignocellulose material. If you have to think like a compound, it has a cellulose and hemicellulose and lignin. Hydrothermal pre-treatment I did in one of my research between 180 to 220 degrees C, and then pre-treated biomass goes for fermentation to make ethanol. But what happens when you use water, you get some of the sugars coming in the water, with water, that we call liquid hydrolyzed. How to utilize this? Because we are losing some sugar here during the pre-treatment. And then when you do the fermentation, lignin will not be fermented, so that comes out, and some of the sugar which are unfermented, not hydrolyzed or fermented well, so that will come as a residue. So how to utilize these 2 points? So I try to address these things in my research. So if you do the water, now I am giving you the ACM picture for switchgrass before and after hydrothermal treatment. You can see there are a lot of open structure here. So once you treat with subcritical water, a structure opens up, and now you subject it to enzyme, cellulase enzyme typically here, and see how much sugar is released. So this is untreated. Take grass and put to enzyme, nothing comes out, just 2.4% of sugar, glucose comes out. But if you treat this grass with 180 degree temperature, you can see that 80% of the sugar, glucan came out after the pre-treatment. So it improved the digestibility of the switchgrass by hydrothermal pre-treatment. Now the liquid you generated, it contains some of the sugar. What we can do, again we can do this, use this liquid by a hydrothermal carbonization, again subcritical water condition, and these sugars can precipitate out as a carbon microspheres. And these carbon microspheres are basically tarry material, you can see, and these are amorphous, contain 65 to 66% of carbon. That means good energy value, higher heating value, as good as lignin. So they can be used as a fuel. Another application I will talk is how to make biocrude, crude-like material, petroleum crude-like material. Yes, we can use subcritical water to liquefy biomass. Take biomass, use subcritical water condition, roughly 300 degrees Celsius or so, and liquefy biomass. And then this crude is basically a bio oil or biocrude, can be upgraded to make hydrogen or critically upgraded to make liquid hydrocarbon fuel. So hydrothermal liquefaction, this kind of term you will hear when you use subcritical water. We can have a biomass and water pumped as a slurry. We can have a hydrothermal reactor where we do the liquefaction. The solid fraction which comes out is called char, and the liquid fraction, crude fraction, and some gaseous fraction will separate it out. And crude fraction goes, it will look like a petroleum crude, but it's not yet ready for the liquid fuel application. So because it needs some more hydrogen to be upgraded and remove oxygen, so catalytic upgradation, and we get naphtha hydrocarbon fuels. This process is called basically hydrothermal liquefaction, liquid fuel biogas. So use of subcritical water is here in the water medium. So what is the benefit? We don't have to dry biomass. In fact, we can use additional water and then we can recycle this water back. In one of the research when I did that, this paper is already published 3 or 4 years back. Switchgrass can be liquefied as low as 235 degrees Celsius in subcritical water to make biocrude, and which is yield was roughly 50%. What helps here, water sometimes cannot be alone sufficient. We can add some acid or alkali to expedite the reaction whatever we want. So in this case I use potassium carbonate 0.158%, little bit of it. And then we see that at different reaction time, the highest yield was up to 50% of biomass can be produced as a biocrude. So this is one of the good applications. So what is the benefit here? We didn't use any solvent, and potassium carbonate, little bit of it to initiate the reaction. And this potassium is also part of switchgrass. So it's much a greener process without use of chemicals, and we can make as a biocrude. Another application, when I told you that when you do the ethanol production, unhydrolyzed solid, majority of lignin and some of the unhydrolyzed sugars, they can be liquefied. And recently I did that, we did that, our group did that in the corn stover, leftover material, and do the hydrothermal liquefaction at 320 degrees C, and you can see that you can get bio oil, two fractions, light bio oil and heavy bio oil fraction. Again, the use was just a little bit of potassium carbonate and subcritical water conditions. So this is again a greener method to do. This result was recently presented at American Institute of Chemical Engineers annual conference at Pittsburgh. We can gasify it. Again, I want to emphasize that if you are looking for the gaseous fuel, syngas and all, it's a wet feedstock. We don't have to dry. Normal gasifier, you need a dry feedstock because water does not contribute. But in supercritical water gasification, water can be used as a reaction medium to gasify. And what is the benefit? The gasification temperature drastically comes down. The conventional gasification is conducted between 7 to 1000, more precisely around 900 degrees C. But supercritical water gasification can be good as 500 or 600 degrees Celsius. Less star formation, clean gases you get because we are using water, so most of the impurities are scrubbed. We can make syngas, and since we are doing this reaction under pressure, syngas comes out as a under the pressure condition directly at a high pressure. So this can go to the Fischer-Tropsch reaction and we can use for the liquid fuel production. So another application in switchgrass liquefaction, we use again potassium carbonate. It helps. This is a homogeneous catalyst and it helps in breaking down the biomass pretty fast. So I'm saying that when we used potassium carbonate and hydrothermal gasification condition, up to 70%, 5% was the carbon gasification efficiency in just use of water. I'm trying to go faster to save time here. So I talked about the liquid fuel, ethanol and bio-crude production. I talked about the syngas production using supercritical water. Now can we make solid fuel? Yes, biochar. What would be the benefit of this kind of char? This biomass comes with a lot of moisture. So we can use that moisture to carbonize biomass and make biochar, maybe at the site where it is generated, and then transport this biochar. What are the benefits? Raw biomass has high moisture retention, so if you leave it open, it's biodegradable faster. But once you carbonize it, low moisture retention. Because of lot of water and oxygen, low heating value. Once we carbonize it, it has a higher heating value, means per kg of char will have a more heating value than the per kg of biomass. High transportation cost. Transportation cost, if you are transporting this, that means transporting roughly 40% of oxygen and lot of water. If we carbonize more like a charcoal, less dollar or less rupees per megajoule cost of transportation. Biomass is perishable if you leave it as it is. If you carbonize, it becomes non-perishable and can be stored for longer time. Fibrous, non-fibrous, poor compatibility of coals. This char powder you can mix with the coal, so better compatibility. So these are the benefits of making solid fuels, and then it can go to refinery and gasify or whatever the other applications. How the heating value changes? This result I am giving from hydrothermal carbonization of switchgrass. We use switchgrass and subcritical water condition, and at different temperature, 200 to 280 degrees Celsius, and different temperature, we try to carbonize switchgrass. And how the heating value of change? The raw switchgrass, which has a 17 megajoule per kg, once you carbonize through use of subcritical water, by tuning the reaction towards not liquefaction but carbonization, we can get up 27 or 29 megajoule per kg, which is as good as bituminous coal. What could be the application? Co-firing application. So there can be one mobile carbonizer at some site. We can carbonize it hydrothermally without drying and get char, bring it to the power plant where it can be used for co-firing, or it can be used for gasification or pyrolysis. And many environmental applications are also there, soil amendment and contaminant removal. So most of the application I talked to you till now was the land-based or terrestrial plants or feedstock. They are grass or woody material. Now I'll talk to the water-based plant feedstock like microalgae, how to use that. So microalgae is, again, what are the benefits? It converts sunlight and CO2 into energy. Advantages are rapid growth. It can grow in wastewater or salty water or marine environment. Does not require arable land, because in the grassy material or woody material we look land, but this can be grown in the ponds and many wastewater plants. It can utilize CO2, which comes from flue gases. What it has is protein, carbohydrates and lipids. Lipids, what we are looking for, and lipid contents is much higher here, because if you have a soybean, oil yield is 48 gallons, sunflower 100, jatropha 200 gallons per acre per year, but with algae, oil yield can be order of difference, 1,000 to 6,000 gallons per acre per year. So these are the benefits of algae. But what are the challenge? So many species, 40,000 known species and many more. How to cultivate, how to harvest? It's a very dilute material. How to harvest it? downstream processing is full of water, nutrient recycling, lot of nitrogen and phosphorus are there. So these are the challenges, and how we can use in. You can see the challenges. Algae, if we grow, this comes so dilute. Concentration typically you will get 300 and 400 milligram per liter, and how it looks. This is one of the open pond which we run here for cultivating algae at Old Dominion University. Showing that picture here. So even if we harvest, what is the challenge here? How to remove this water? And typical thermal dryers use more energy per kilogram of evaporator, roughly 3.3 to 4 megajoule per kg can go just removing water. So is there any process where we don't have to remove this water? Can we use this water? Yeah, hydrothermal technology can be one of the options here. It contains proteins, that means a lot of nitrogen. If you don't remove these proteins or nitrogen, that means what's going to happen is going to the fuel. So that's another challenge. Can we use this protein to make another bioproducts from it? Nutrients management, because it contains protein, that means a lot of nitrogen and phosphorus. And to grow microalgae, we need these nutrients. So can we recycle that? To give you an example, 1 metric ton of dry algae if you want to produce, typically it can be more only, this is the conservative estimate, 80 to 90 kg of nitrogen and 10 to 12 kg of phosphorus are required. If you don't recover or recycle this, it's going to be a strain on nutrients. So if we use hydrothermal technology, in these cases, because it comes in water, so subcritical water or supercritical water condition can be used to make syngas or biocrude or biochar. So what is important? It is important to develop a process for 100% utilization of available biomass, company which can produce fungible fuel, means advanced biofuel, and bio-based products also. So what is our approach? This is one of the study I am presenting from my lab group done in the last 2 years. We developed a process which call it flash pyrolysis under subcritical water condition in a continuous process reactor, continuous flow reactor. Algae can be fractionated in 2 phases. One is liquid rich phase, and the liquid phase is mostly protein rich phase. So now what we did that, we remove most of the nitrogen as amino acids or peptides. And now the lipid rich phase can go for the biofuel production by catalytic degradation, and the protein phase can be used for bioproducts or nutrient recycling. So this process we have filed a patent also recently. So this is the step we are taking. And our approach is develop a process, continuous process, where we can do the extraction in the first stage based on the reaction, based on the depolymerization kinetics of proteins. We can hydrolyze them in the liquid phase, and lipids we can protect them, and that can go in the second stage to make hydrocarbon fuels, and the water, excess water, can be recycled back. So this is our approach, and I'll try to show you what we have here. We have here 1 acre open pond where we grow algae. We call it Norfolk Virginia Coastal Energy Research Consortium. This is a consortium of 7 universities, and we run here one of the pilot reactor to make biodiesel. And then we grow algae to do so many other research and understand the environmental implications, processing implications, harvesting implications, and all. In my laboratory, we have this setup, that continuous flow reactor setup, where we can use algae slurry and do the fractionation or liquefaction or gasification, so many applications. So my point I would like to conclude with this, that our approach should be, when we are looking for biofuels, our approach should be minimum chemical footprint. So use of water, sub and supercritical water, temperature and pressure conditions, to make the conversion process more greener. I gave you the examples how it can be. It cannot be always just water. We might need to use alkali or some heterogeneous catalysis and all, but still, as much as we can use this technology, it gives you much greener option because water is non-toxic, environmentally benign, and inexpensive. And this is our approach. And with this, I would like to thank you for giving this opportunity. And I feel sorry that I ended up taking some extra time here than the allotted. Thank you very much, and I'll appreciate your questions.
You are currently the only person in this conference.